So this is joint work with two students of mine, high school students, very smart ones, HUN-REN and Ismailescu. Now the starting point of our journey is a very famous problem, probably one of the most famous problems, open problems in our field, the chromatic number of the plane question, raised by Nelson apparently, somewhere in the 1950s. Was the number of colors required to color the plane so that no 2 points unit distance apart have the same color. And the stuff we know is very limited if we are to speak in strict terms. We know that you need at least how do I turn the pointer on? Oh, all right. Ah, okay. So this is the Moser's spindle. No, that's not a mistake. There were two brothers, so that's why I wrote it that way. So you saw this already in Conrad's talk, and this requires 4 colors. And on the other hand, you have an equally simple construction due to Hadwiger that shows that 7 coloring is possible. And not only that, but somehow to make things more interesting, you have a lot of freedom in changing this coloring. And the reason is that if the side length of a regular hexagon is x, then the diameter of a tile is 2x, and the distance between two identically colored tiles is x root 7. So what you want is to have 2x smaller than 1, and x root 7 bigger than 1. So you avoid distance 1 within each color. So that gives you a range for x between 1 over root 7 and 1/2. So you have quite a bit of freedom. So the question is, can you actually do something to take advantage of this freedom? So for instance, in this case, all the colors contribute pretty much the same, actually exactly the same percentage. 1/7 is the density within each color. So can you actually try to squeeze one of these colors and kind of make the other ones bigger? And the answer is yes. And the result we have is an improvement of previous results of Pegg and Pritikin. So let's read the statement. You have a tiling of the plane with decagons, rhombi, and triangles, such that each of the decagons can be assigned one of 6 different colors, and no identically colored points at distance 1 from each other within any of these 6 colors, while the rhombi and triangles occupy a fraction of 1 over 6400 of the entire plane. So basically we have 6 colors, and the 7th one, actually we have 7 colors, but the 7th one is used only very sparingly. And this is the picture. Now, so let me explain a little bit what I'm doing here. I start with a tiling of the plane with pentagons, so it's a double lattice tiling. You have one row, you have another row here, and then they're symmetrics. But of course, and that uses only 6 colors, but that doesn't work. You're going to have distance 1 in all the colors, actually. But what you do next, you chop off, for each of the pentagons, you chop off a little bit from each of the corners. You chop off a little bit of from each of the corners with 2 things in mind, actually 3 things in mind. You want, on one hand, each tile to be of diameter at most 1, so you don't want to reach distance 1 within 1 tile. On the other hand, you want the distance between 2 identically colored tiles to be at least 1, so you cannot get monochromatic distance 1 with 1 point in one tile and 1 in another. So you see here, these 2 are parallel lines. The width of this strip is 1, and then the distance from this tile to this tile is the width of this strip that's represented with dotted lines. So you want to chop off a little bit here and a little bit here so that the width of this strip is 1. So now the amazing thing is that all you have to chop off is this fraction to achieve both these conditions. So the picture is not drawn to scale. These pieces, these white pieces that are left uncovered, are shown, so triangles here and rhombi is here. These are much, much tinier. It's the white part is just this much. So in other words, you can 6 color 99.984% of the plane while avoiding distance 1. So what's left is the hard part, the remaining 0.016%. All right. Well, so this comes close, but really, in math, if you come close, it's as if you never get there. So Seufer asked, well, what if you are allowed to use 6 colors? Can you say something relatively meaningful? And he came up with this nice result. You have a 6 coloring of a plane, and ideally you would like all 6 colors to avoid distance 1, but he came up with something else. He said 5 of the colors avoid distance 1, and the 6th color avoids some other distance. And actually he was able to produce an entire interval, which is a small interval. This is 0.41, this is 0.43. So for any d in this very small interval, he came up with a coloring of the plane with only 6 colors, so that 5 of the colors avoid distance 1, and the 6th color avoids this special distance d. So here's his coloring. His coloring is inspired apparently on the Russian bathroom tile pattern, so I guess it somehow helped that he was aware of this. So the tiling consists of octagons and squares. So it's a pretty nice tiling. And again, every octagon is a centrally symmetric octagon and is obtained by chopping off appropriate triangles from the corners and then putting them together in this lattice-like manner. Again, you want the diameter of each octagonal tile to be 1. You want the distance between 2 tiles identically colored to be also 1, and you want the small squares to have diameter d and the distance between 2 such squares. So the 6th color is the white one. And you have to be a little bit careful how you color the boundary, because you don't want to achieve distance 1 within the closed sets, but it is possible. It can be done. It's not complicated. So with 6, Seufer calls this type of coloring a 1-1-1-1-1-D coloring, which means each of the first 5 colors avoid distance 1, the 6th color avoids distance D. And one nice question would be to try to expand on this interval. Can you actually prove the same type of results for D's outside this interval? Apparently, it's not that easy. Now, we go back to a question from a famous paper by some famous people. So Erdős and the company asked in 73, if you have a 3-point set in the plane and any 2 coloring, then that coloring is going to either contain 2 red points unit distance apart or a monochromatic white copy, actually translate of T. So if we are thinking at the only 2 colors rather than 6 colors, then one of the colors avoids distance 1, the other one you have so much freedom that you can fit any translate of some given triangle. And they couldn't solve the problem if you replace the triangle by unit square. So you have a 2 coloring, one of the colors avoids distance 1. Is it true that, in the other color you have a copy of any given unit square, of any unit square? And this was proved to be true a few years later by Juhas, who actually generalized, strengthened their result, the intended result, and who proved that for actually any 4-point set and any 2 coloring of the plane, you find either 2 red points unit distance apart or a white copy of the 4-point set. And it was reasonable to ask, well, how much can you push this? 3, 4, can you do 5, can you do 6, can you do 7? Well, we don't know, but Csikszentmihalyi thought sometime after that, proved that you cannot do 8. So here's the result. You can find the two coloring of the plane and an 8-point configuration, a regular heptagon in its center, such that one of the colors avoids distance 1 and the other color avoids this 8-point configuration, in the sense that you cannot have a monochromatic copy of H all in white. So this is their construction. You start with coloring some circles centered at the lattice points in red. So each circle has diameter 1. The distance between any two circles is 1. So that's these open circles. The red set doesn't achieve distance 1. And then they consider this 8-point set configuration, a regular heptagon and the center, and they take 0.9 to be the radius. Why? Well, because it works. So here is one attempt of trying to place a copy of the 8-point configuration on top of the white-red coloring so that all 8 points are white. And you see that you cannot do it. I mean, 7 of them are white, but the 8th one is inside the red circle. So no matter how you try to move this thing, rotate, it's always going to be a red point of the configuration. So one of these 8 points is going to land on a red circle. So you may ask, what do these two things, Seufer's problem and Erdős problem, have to do with each other? Well, they have everything to do with each other because they are two particular instances of this particular problem. So you have a number of colors, somewhere between 2 and 6. Already for 7, Hadwiger's construction does the trick, so we don't have to worry about that. So you have a number of colors between 2 and 6. You want to find the coloring of the plane with that many colors and a finite point set K, such that the first R-1 colors, each one of them avoids distance 1, and the final color, the last color, avoids a monochromatic copy of K. So if you think for a second, there exists a 2 coloring of the plane on 8-point set, so that the first color avoids distance 1 and the second color avoids K. Well, this is exactly Toth and Chismadia's result that I mentioned earlier. And then there is a 6 coloring of the plane and the 2-point set, K, pair of points at distance D, where D is in that interval, such that 5 of the colors avoid distance 1 and the 6th color avoids K. And that's exactly Seufer's result that we saw originally. So the question is, of course, what happens for 3, 4, and 5 colors? Makes sense, right? And as you can see, we prove something very, very similar, I mean, in the spirit. And the higher the number of colors, 2, 3, 4, 5, 6, the smaller the size of the configuration that we can prove that cannot appear monochromatically. It's 8, 6, 4, 3, 2. Okay. And the constructions are really not that difficult, so I'll show you a few more pictures. So this is I'm going to do things a little bit out of order. This is a result for the 5 coloring. So you have 5 colors, let's call them red, blue, green, yellow, white. And the 3 points at the vertex of a triangle, such that each of the first 4 colors avoid distance 1 and no monochromatic triangle in white appears. So this is a very reasonable approach. You try to color as much of a plane as possible with the first 4 colors so that you have very little space to maneuver with the 5th color. And that's, the most natural thing you can do. Now you see that the points of tangencies are colored kind of carefully, and you'll see in a second why. And it's very easy to guess that this little triangle here, created in the white space, cannot actually have all 3 vertices white, and that's why you have to be careful when you count the boundary. So you don't want this, this, and this to be all white. So you have to kind of alternate the colors to destroy, some of the white points between when the circles are tangent. Okay. So we can prove that, and actually, it's not a difficult proof, that you cannot actually fit one such triangle, all whose vertices are on the white spots. So now notice that in the first 4 colors, more than 90% of the plane is covered. And again, that was reasonable to do because you wanted to restrict yourself as much as possible in the white. But here's another example, which is kind of surprising because basically you have 50% of the plane is white, and you still cannot fit this type of triangle. So you have, again, 5 coloring: red, green, yellow, blue, and so on and so forth. And you basically do this strip coloring. You leave every other strip white. And of course, now if you try to fit this equilateral triangle whose width is exactly √3/2, well, you're not going to be able to do it because the boundaries, these strips are closed, so their boundaries are already colored in blue, green, red, or yellow. So you cannot actually fit all 3 points to be white. So these are now what's interesting is for 5 coloring we have 2 different constructions, but in each case the forbidden triangle is equilateral. So we don't know of any other configuration that can be blocked, 3-point configuration, any other triangle that can be blocked in this particular manner. So that's maybe a question that's worth looking into. 5 coloring of the plane, 4 of the colors avoid distance 1. Find a non-equilateral triangle that cannot appear monochromatically in the 5th color. All right, here's the 3 coloring and the corresponding result for 3 colors. So this time you use a square lattice, and again the diameter of each circle is 1. The distance between 2 identically colored circles is 1. So this one is √2, the side of the square in the square lattice. And you pick the 6-point configuration to be this one, a regular pentagon with the center. And that's kind of reminiscing of what Chismadi and Toth did in their paper. Regular heptagon in the center. Why 4/5? Well, because 4/5 works. So the idea is that no matter how you try to place these 6 points in this 3-colored plane, you are always going to have a point which is either red or blue. So it's impossible to have this 6-point configuration all in white. And if I'll have time, I'll tell you how to prove this. But now, for 4 colors, this was the trickiest one of all, so that's why I left it for the end. So you want to color the plane in 3 colors, 2 of them avoiding distance 1. Sorry, in 4 colors, 3 of them avoiding distance 1, and the 4th one avoiding some small as possible point set configuration. So again, it's kind of reasonable to start with this 3 coloring of the plane. Actually, 4 color: green, blue, red, and white. White is the 4th color. And again, it's kind of natural to expect that, something like equilateral polygon plus the center does the trick. But it doesn't. It doesn't because if you place the center of the equilateral triangle right here, since the triangle has 3-fold rotational symmetry, and so does this particular covering, as soon as you're going to have one white point, you're going to have all 4 of them, all 3 of them. So this doesn't work. So there is actually a way to do things, and you have to kind of be a little bit, to tinker a little bit with the problem. But it's still, a 4-point configuration, triangle. The triangle is not equilateral, and the point is not quite the center, but this works no matter how you try to place this. You're going to have one of these points landing on a green, red, or blue spot. I would like to thank everybody for being here so late in the conference, and thank the organizers for their wonderful efforts with wonderful results. Thank you.